Gave me. Good evening, everyone, and welcome to this year's Organic Lecture. The full name is the Elliott Organic Memorial Lecture. And so I'm going to say a few words about Elliott Organic to get started. So I'm Mary Hall, the director of the College School of Computing. And this event tonight is the highlight of our year. Every year, it's our lecture that where we bring, a remarkable speaker in. And this year, we are very fortunate to have a speaker that was an alumni of our program. So I'll let him tell you about that in a minute. So Elliott Organic was trained as a chemical engineer, and he is known for his leadership in really founding computer science education. In 1960, he was teaching computer science to high school teachers. And in 1961, he wrote his first book. It was on Fortran, on the Fortran language. And then he went on to write a total of 19 books, a very popular intro to computer science book, books on programming languages, computer architecture, and a very well-known book on the Multics operating system. And then in 1968, he led a group that of computer science researchers that created what is now called the ACM-SIGC, the Special Interest Group on Computer Science Education. So that's the premier organization of people interested in computer science education. And then he moved to Utah in 1971. So he was hired to revamp the computer science curriculum. And it was the curriculum for a long period of time. He did a bunch of other things in terms of leading CS education. He had a regular computer science education article in the Communications of the ACM, which is a magazine for our professional society. And he was the founding editor of the Computing Surveys journal. And so for all of this work, for these contributions, in 1985, he was awarded the 60 Outstanding Contribution to CS Education Award. And so we are I feel like our commitment here to computer science education was really, that foundation was laid by Elliott Organic. We are very honored to have a bunch of members of the Organic family in our audience tonight, and they'll be joining us later. Yes. So we have two of Joe's sons, Elliott's sons, Joe and Alan. Joe's daughter, Lee, Alan's son, Elliott. And then we also have, they brought with them a guest, a former department chair's wife. Mary Johnson is here, Bob Johnson's wife, and their daughter, Perrine. And we're very grateful to the Organic family because they we had an endowment for this lecture, longstanding endowment for this lecture, and they enriched that endowment so that we can make it the kind of event that we're having tonight. So thank you, Organic. You're going to be very happy with the lecture tonight. So I am going to ask Tom Henderson to come up, and he's going to introduce our speaker.
Thanks, Mary. This going? So it's also an honor and privilege for me to be here tonight introducing Alyosha. And welcome to the Organick family and to Mary and Perrine. And so I recall Perrine's a ski buddy of my wife. So this is a tight-knit community. So what I wanted to let you know first was that this probably isn't a normal introduction. Why? Because in 1992, some East High School student came and said they wanted to work on, what was it? Parallel computing. But on what topic? Polymer simulations for some professor in material science. And I said, okay, sure, why not? And this was Alyosha. And then I started getting this kind of email from him. Oh, guess what, Mr. H? I'm going to direct a play. So I learned that he's actually an Anton Chekhov follower. And it was great. So I knew he was somebody to watch out for. And so he joined my group as an RA. And this is from a robot competition we did way back when, probably in Portland, Oregon or something. And believe it or not, that guy sitting down in the middle is me. But Alyosha was the heart of this project. And in fact, we had a robot, that thing on the right, which he helped put together, program, software, hardware, everything, simulate it, run it. And of course, since he was the daddy of that thing, he got to name it Igor. And we had a lot of fun traveling places, doing all kinds of stuff. And we actually placed third in one of these competitions and got into Alan Alda's science show as a robot that could find tennis balls. All right. Anyway, of course, there was life after here, and he did get his education here. I highlighted that. And then he went some other places. All right. But the foundation was here, and I think it was good. It was kind of an enlightened area when we had a lot of things going on, a lot of opportunity, a lot of people here that were doing some stuff. He's worked at CMU as a prof and then went to Berkeley, and he's there now. What's he interested in? And I am wrapping up. Okay, I know it's his talk. As far as I could tell, understanding human visual intelligence. So this is kind of contrary to large language, let's say it'd be large vision kinds of models. And he has had a lot of vision, working in the areas of computer graphics and computer vision, and has won a lot of prizes and been recognized for a lot of that work. In fact, this is not only technical recognition, he gets teaching awards. So Elliot would be particularly happy, I think, to have someone who's a product of the program here who actually excels in those areas. His areas he'll talk a lot about. I won't spend any time on it, but basically data-driven methods. And I thought I would also mention in passing that this is the Elliot Organic Lecture. Well, I knew Elliot. He was here when I got here in '81, again. And he was a friend of me. Took me to New York to visit a company to work on something new, object-oriented programming with Ada. And I learned from him. He was a mentor. He was a computer scientist, got me into logical, I called it logical sensors, which is another form of that sort of work. And he was a great computer educator. So I'd like to welcome the family. And I know Mary's here now and Perrine, so welcome to you guys too. And with that, I'll hand it over to Alyosha.
Thank you.
We only got 2 minutes left.
Ah. Okay. Yes. Okay. I'm very honored to be here. I did not know that Igor was going to make an appearance. I'm very honored to be back in at the U, and very honored to be giving this organic lecture. I remember going to several of the organic lectures when I was an undergrad, and I remember that it was always a treat. So hopefully I can pay back. And let's see, is it not? Start this thing again. Okay. And I just wanted to say that the U was a magical place to do an undergrad, at least back in the 90s when I was there with some of the folks that went there. And it was really, I remember skipping to class for every single day. It was just so fun. And I had wonderful research mentors, Tom, Pete Shirley, the late Bill Thompson, that taught me so much. And it's amazing that an undergraduate could get this amount of mentorship. And also just wonderful classes. There's so many wonderful teachers that I still remember to this day. And interestingly, did you know that in the 90s, every sophomore in the CS program at the U coded a large language model? Hard to believe, but it's true. Joe Zachary's random writer project was basically okay, maybe not large language model, but a medium language model, way ahead of the time. And in fact, it was so influential to a lot of us that, my PhD at Berkeley was basically based on that project, but doing it for pixels rather than words. And I thought that maybe I should start with basically kind of connecting the dots for you. So the key ideas of these large language models, they actually are very old. They go back to all the way to Markov and Shannon. So Markov in 1913 wrote a paper on analysis of statistical patterns in text. So he took the Pushkin's Eugene Onegin, and he basically counted what was the distribution of vowels after a consonant, okay? And then Shannon in 1948 took that idea of basically using a Markov chain to model language to say, we can generate English sounding text using the idea of a Markov chain, an n-gram, okay, a generalized Markov chain. So basically, he assumes that our language is Markovian, okay, and then he says, okay, let's just compute probabilities for every set of n letters, what is the probability of the next letter? And just count, you take a very big book and just count those probabilities up, okay? And you just add them all up, okay? And then once you have all of these probabilities, now you can start with some initial seed, and then you can just sample from that Markov chain to generate one letter at a time. Now, this maybe sounds very technical, although, again, this is freshman kind of a task, and you also can do it for words as well. So we can do this all together. Let's start with a seed of 2 words. We need. And then we go, okay, what is a likely word after we need? It's probably some small one, is like the, to, right? So let's say that it picked 2. Now you shift your context and say, okay, need to. Now, what is a likely word after need to? Probably some sort of a verb, probably some sort of a common verb. Need to sleep, need to eat. Okay, eat. Okay, now you shift again. And if this is a book on French Revolution, then probably cake is pretty likely. And there you go. You just generated your sentence just like we did as freshmen in Joe Zachary's class. Okay. Now, and this kind of things were actually pretty good. Okay, so these are some of the pearls that Joe ran a competition about the funniest things that it generated, and these are the kind of things I spent an interesting evening recently with a grain of salt. Right, so the texture of the sentence is actually pretty good. It's just that it doesn't quite make global sense. Okay, so what is missing? Well, the problem with these kind of n-gram methods of n-gram of Shannon's was that your window, your context window, like in my example, it was 2 words. So your context window is fixed. So what is the problem with a fixed context window? Well, if it's too small, then the end of the sentence doesn't know about the beginning of the sentence, and you get this kind of a, you change topics midway. Now you could say, okay, let's make the window bigger. But when you make the window bigger, it becomes too large, and then you run out of data. Okay? And basically, the solution to this problem is to say, okay, I'm going to have a dynamic context window. I'm going to have a really, really long window, but I'm only going to pay attention to some of these things in that window. And that is basically what modern transformers with self-attention are doing. So basically, what Joe was having us re-implement is really, really close to the GPT and all the other ways that are now very hot in generative AI of generating text, generating pixels, generating audio. It's basically that story scaled up and applied to a huge amount of data. Okay, so I think that is kind of the shortest explanation of generative models you have heard so far. But I think it's a very reasonable one, given that kind of you understand the simple things that where it came from the Shannon's ideas. Now, I think for me that my undergraduate education at Utah really was the start of really appreciating the importance of data. And I felt like, okay, by now everybody else has also caught up. The data, everybody appreciates the importance of data. So why am I giving another talk on the importance of data? Well, I keep looking at these things on the internet that my students are interested in. And for example, there's this thing out of OpenAI that came out this summer, a very, very long document about the future of AI. I'm not asking you to read it. I'm just going to Wordle summarize it for you. So you have the usual, the AI, AGI, GPT, models, progress, years, decades, automating, blah, 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 right? You can imagine what this is all about. But the annoying thing for me was that, where is data? Right there, tiny little thing. So it feels like, okay, maybe we're appreciating the data more than we used to, maybe still not enough. Okay, and so this talk is really about maybe convincing you that much, if not all, of the magic that you're seeing right now in this AI renaissance is due to the data. Okay, so let's start with art. Let's start by transporting ourselves to Paris. This is Musée d'Orsay. This is Monet's painting Gare Saint-Lazare. And you feel like you're in this. It's a very nice painting to really make you feel like you're in this turn of the century train station and the hustle and the bustle. And there's this steam engine arriving right at the viewer. It's coming right at the viewer, the steam engine, right? Everybody see that? Everybody see the steam engine? Really? I mean, look at this splotch of paint. Like, looks more like a penguin or I don't know, a bottle of champagne and right? Where is the steam engine? But the steam engine is not in the pixels. The steam engine is in our heads, and probably each one of you perhaps sees a slightly different version of that steam engine depending on which steam engine museum you went to as a child. Okay, so this is very, very important. We hallucinate a lot of what we see. So this is a very blurry video of my friend Rob Fergus back in his old days in MIT. This is a video by Antonio Torralba. And it's very blurry, but you guys have no problem understanding what Rob is doing here. In fact, you're doing maybe a little bit too much understanding, because actually Rob is talking on his shoe, and he is going to be computing on his trash can, and listening to his beer cans, and check out the mouse and the printer, okay? So again, a lot of what we think we perceive is coming not from the pixels, it's coming from our memory, okay? So neuroscientist Moshe Bar says, our perception relies on memory as much as it does on incoming information, which blurs the border between perception and cognition. And Lance Williams like to say, mind is largely an emergent property of data. Okay, The thing is, though, that at least in the old days, somehow data did not really get that much respect. Okay, it was all, algorithm was king. It was all about the algorithms. You want to publish a paper in some conference, you come up with a great algorithm, you work on it for a year, then maybe you add some features to it, and then maybe like a few days before the deadline, you say, oh, I need to run it on some data, and download some data from somewhere, it doesn't matter, right? And that kind of mentality has, I feel, slowed us down in many ways. So I'll just kind of go through some examples of this. And this first example comes from computer vision, my field. And this is when I was an early graduate student in the late 90s. Computer vision was a kind of a depressing area in the 90s. Just nothing worked. It was very cool, very exciting. It just did not work. And then there came a time when, boom, something started working. And that something was phase detection. Within a couple of years, phase detection just felt like it was solved. It was in all the cameras, and it was really kind of dramatic. And so for those of you who maybe have taken a computer vision class, can somebody tell me what is the paper that kind of the key paper that felt like, okay, that paper solves phase detection? Any computer vision folks here? Eigenphases is phase recognition. I'm talking about phase detection. Viola Jones, does that ring a bell? Exactly, boosted cascades. That's what everyone remembers. That is what's in all the textbooks, but it's not really true. Actually, there were 3 papers. The first one was Raleigh-Baluji-Kanadi. The second one was Schneiderman-Kanadi, and the third one was Viola Jones. All 3 are very well respected, tons of citations. All 3 got the Test of Time award. Everybody, all the 3 papers felt very important. Why is it that we remember Viola and Jones? My feeling it's because of this bias towards algorithms. Because Raleigh-Baluji-Kanadi was using this very, very old technique from the 80s called neural networks. It was kind of embarrassing back then. It's like, oh, this is so old, not sexy, right? Then, Schneiderman-Kanadi, okay, naive base, kind of naive. But Viola and Jones, boosted cascade, it's a beautiful algorithm. I still teach it in my machine learning class. It's just that it didn't seem to matter. They all were doing pretty similar, actually Schneiderman-Kanadi was doing a little bit better, but they were all doing pretty much the same performance. And really, the main reason why these works were doing so much better than the stuff that before was that these were the first papers that realized that in addition to positive data, images with faces, it was also very nice to also have negative data, images without faces. And that's actually what made these things work. But somehow in our kind of scientific memory, we kind of forget this part. So I call this our scientific narcissism. All things being equal, we prefer to credit our own cleverness, the algorithm, rather than data, because the algorithm comes from humans, and we can think about being creative, whereas data is just sitting over there, right? And that maybe has kind of been pushing us back, because there is a lot of kind of magic that's hidden in the data. So there's this wonderful short paper called The Unreasonable Effectiveness of Data out of Google, and where they basically argue that parts of our world are very nicely explained by elegant mathematics, physics, chemistry, astronomy, etc. But there is other parts of the world, kind of the more biological, more evolutionary parts of the world, that don't really have a good elegant mathematics behind them. Psychology, genetics, economics, AI. These are the things that don't really fit very well this mathematical mold. And these are exactly the areas where we observe this magic of data. Okay, so why this is? Well, because evolution is messy. Okay, and as soon as you look at evolutionary processes, there is just a lot more stuff, a lot of more random stuff, lots of entropy that just starts to pop up. So imagine if you're doing, you're doing computer graphics and you want to simulate smoke in some movie, right? Well, this is something that computer graphics does very, very well. Simulating smoke, you take your Navier-Stokes equation, you throw it into a simulator, and you have beautiful, gorgeous smoke. SIGGRAPH papers have been doing it for 40 years now. It's a solved problem, and it looks very, very realistic. Okay. What about simulating the pattern of bark on this old tree, on the other hand? Now, that is something that's extremely hard. Is there some equation that somehow simulates the pattern of bark? Well, perhaps there is, but that equation will have gazillions of parameters because it will have to have the genome of the tree, the weather conditions of the tree, whether there are the squirrels nested in this tree. Like, a lot of parameters will have to take in, and still we might not get a very good representation because there is just a lot of randomness that also happens. And instead of dealing with all of that very complicated parametric representation, an alternative approach is to just take pictures of a lot of trees, okay? And just have the data tell you what a tree looks like. And that is fundamentally what data-driven approaches are about, okay? And the good thing is, now we have the data. In fact, we have a data deluge. We have too much data. So conditions are perfect for this kind of data-driven exploration. And what we find is that with enough data, some stupid brain-dead lookup, technically known as nearest neighbor classifier in machine learning, works surprisingly well. Okay. In fact, here is some of my work from back in the day in 2007, where we said, okay, let's say we have an image and we want to edit it. We want to kind of get rid of this thing, and we want to fill in the hole. So how do you fill in the hole? And the idea is, okay, just download a couple of million of images from the internet, just random images, and then just find the closest images to the one that you need to fill in the hole, something like this. And then, a little bit of computer graphics magic, and there you go. Or you can take the next closest image and you get something like this. Or you get third closest image, get something like this, and it slowly gets maybe not so good, but you get to see the point. Okay. So here's another thing. Okay, you don't like the view from the window. Okay, get rid of that. Okay, here's a better one. Okay. Or you don't want this development on your favorite beach. Get rid of that. Okay, here we go. Okay. And why does this work? Is it the cool algorithm or the cool feature for representing these images? Well, not really. What happened, when we started this project with my graduate student, James Hayes, we thought, okay, we're going to create the largest data set of images ever. And so it was about 20,000 images, which was, 20 times greater than the largest data set at that point, okay? And then we did this kind of nearest neighbor, finding closest images. None of them were very, very close, right? So it basically was kind of like a failure. And then it was around December. And so I told James, you know what? We're going on a Christmas break. Why don't you just keep the computer downloading images while we're on a break? Just keep downloading for a few more weeks. So when we came back in January, we had 2 million images and exactly the same algorithm. No change in code at all, just started working. So somehow, if you have enough data, it starts to whisper in your ear. This kind of magical way, okay? And and why is 2 million is enough? 2 million sounds like, okay, maybe it's even that is maybe not that much. Well, it's not that much, it's true. But the thing is, like, for example, for this image, let's say we want to get rid of this crane, okay? That works very well. Let's look under the hood. Okay, these are the kind of the closest matches to this image. Let's look at the first one. Look at that. Look at that. So this is a different city. This is a different river, and yet it looks so similar. So why is this? Well, first is because we humans are boring in that we always build similar things. The French architects look, okay, you have a river, you have to have some, nice embankment, and you have some nice view buildings to look at the river. Okay, but second, we're also boring as photographers, because you go to France, you walk across a bridge in Paris, you turn right and say, oh, what a beautiful view. Ka-ching, say you and 10,000 other people, right? And so all of these kind of patterns, they're all good for us, because they mean that the data is kind of clustered in kind of exactly the right way, okay? And then our next paper was like, okay, can we do something more with this trick? And so we thought, okay, can we, for example, guess where this image is in the world? Can we put this image on the map? So this is like, this is the precursor to GeoGuessr, right? Now all the kids are into GeoGuessr. So this was computer trying to do GeoGuessing, okay? Into GPS, we called it. And the exact same idea. So we downloaded even more data, 6 million images. And then we said, okay, just find the closest matches and then let them vote using their GPS coordinates on the map of the world. And wherever there is the biggest bump, well, that's your answer. And in this case, actually, it turns out to be southern Utah, and that is actually correct, okay? So it actually worked surprisingly well, okay? Now, fast forward 15 years later, neural networks come into the scene. Big fancy people from Google, they decide, okay, let's repeat this study, but now we're going to use the big neural network machinery, okay? And so they had a paper called Planet, and it used the neural network, and it has also much more data, and it did much better. Okay. Now, luckily, this paper got to me for review, and I'm like, wait a minute here. You guys are changing two things at once, right? You're changing the algorithm from nearest neighbors to deep network, but you're also changing the amount of data. So can we see an ablation where you only change one thing and not the other? And the authors very kindly said, oh, yeah, absolutely. And turns out, if you match the amount of data, then the fancy schmancy Google neural network of the day was basically doing as well as my student James Hayes's hacky feature that he hacked up. In fact, in some regimes, it was doing a little bit better. The James Hayes stuff, right? Now, so what does this mean? I'm not saying forget neural networks, you should just use nearest neighbor for everything. No. Neural networks have other wonderful qualities, but the point here is that the neural network didn't need to do much, right? The neural network was really just essentially doing a fast retrieval of the data that it saw. So it's always important to kind of understand where are the smarts coming from? Are the smarts coming from the algorithmic side, or maybe they are just coming from the fact that you need a lot of data, okay? So the good news is really stupid algorithms plus lots of data gets you this unreasonable effectiveness. But someone should probably ask, wait a minute. This does not seem, especially for us who are, interested in, biological plausibility. Can humans really remember millions and millions of images? That sounds suspicious. Well, luckily, my dear friend Odd Oliver at MIT has an answer to this very question. She was interested in the capacity of visual long-term memory. And actually, she started with some older work by Standing in the 70s, who actually showed that people have a surprisingly good visual memory. In Standing showed that 10,000 images, people were able to remember something like 83% of those images. Now, the problem was that in Standing's experiments, those images that he showed the subjects were very, very different. So there was, a beach, then there was a kitchen, there was a bathroom. So one could imagine that maybe you just need to remember like a few keywords and you don't actually need to remember the whole image. And so Odd said, okay, let's make this harder. Let's make the type of images harder. So we're gonna have kind of this repeat the standing setup where you have different objects of different categories. So that's kind of should be pretty easy. But then we also have setup where we have the same category, but different instances. Or we can have a setup where it's the same category, the same instance, but maybe some change of state, like on the right there. Okay. So how do the humans do here? Well, I think this is one of those examples which is much better to do it yourself than to be told. So we are going to do a little psychophysical experiment, short version. Okay, so ready for some interaction here. We are going to show you a series of images very fast. And when you see an image that you have seen before, you're going to clap. Okay? Okay? If you see something for the first time, no clapping. If you see something you have seen before, you clap. Okay? Are you ready? Okay, they're going to be very fast. So are you guys ready to clap? Okay, let's do it. All right. So I think you already get a sense, maybe, but let's do another test. So what they did is they also did some tests afterwards, after the 5.5 hours. Which one did you see, A or B? Very good. Which one did you see? Look at that. Which one did you see? Very good. Okay, so I think now maybe the results that you're going to see would not surprise you too well. First, it's match or even beat the standing result, 92% performance. But interestingly enough, when you look at what happens at the harder scenarios, it's basically pretty much as good as that. Okay, so there is a little bit of a drop, but it's not a huge drop, which is quite amazing, right? Those two remote controls, right? They like really to tell between them, you really need to remember quite a bit of information, right? So this is kind of amazing. Now, does this mean that we all have photographic memory? Well, good question. They did a study for this. Unfortunately, they didn't even publish it. So I'm kind of advertising their old unpublished work that really they should publish. So what they did is that they said, okay, let's throw in some random textures, visual textures that have the statistics of natural images, but without any of the semantics. So these are kind of random textures that they tried, and they basically did another experiment throwing those in. So one more experiment for you guys. Okay, ready? Okay. All right. So as you noticed, we don't have photographic memories. Something else is going on. So we do very well on things that somehow are on the manifold of natural images, and we're basically at chance for these random textures. Okay. So this is kind of very interesting kind of gives us a little bit more understanding about what is it that we humans, we do use a lot of memory, we do remember a lot of things, but we remember it in some sort of a latent way. Okay. Now, the raw memorization, nearest neighbor methods, they're great. They're the first thing to try, but they have trouble with rare events. If something didn't happen or something happened maybe 1 or 2 times, the kind of these nearest neighbor methods will have trouble finding them, right? And that's really the fundamental problem with this kind of direct data-driven methods, non-parametric data-driven methods. But what we have now seeing in this modern generative models is that these models are able to somehow interpolate and compose data from different sources. And so even if you have something that's very, very rare, these models can still make sense of it by kind of using analogies from different parts. And these generative models like DALI and Stable Diffusion and RT, Sora, et cetera, they're giving us some hint about being able to somehow use the data, but in a combinational sort of way. So for example, these are kind of classic examples from DALI, where you ask it for, a dolphin in an astronaut suit. And of course, there is no data for dolphins in astronaut suits, but somehow it's able to composite data of dolphins and data of astronauts, put it together, and it kind of makes sense. Okay, so this is really quite amazing. But I'm a little bit worried here that again we're saying, oh my God, these are these amazing algorithms, and and these amazing language features, and yeah, there is also some data. Because it might be we're falling for the algorithmic trap again. And so here is I did a little experiment. So this is a text-to-image models, 3 different text-to-image models. I gave them all the same prompt: squirrel reaching for a nut. And all 3 models did pretty well. In fact, I think maybe you prefer one to the others, but they're all doing something reasonable. And the thing is that these 3 models, they have completely different algorithms underneath them. So the first one is DALI, diffusion-based. The second one is auto-regressive, basically kind of a pixel version of a GPT called Parti, Google Parti. And the third one is actually completely different. Again, it's a GAN-based method. Okay, so the algorithms completely different. The objectives kind of different, but similar data and similar quantities of data. In fact, my former student Tae-Sam Park has this wonderful graph where he basically graphed a lot of these generative models by the quality of images that they produce. This is on the y-axis, the FID score. The lower the more realistic the images look, and on the x-axis is the model capacity. Basically, how many parameters are in the model, which means how much data is it able to absorb, right? How much data is it able to take in? And what we see is basically it doesn't really matter what the algorithm is. It basically matters how many parameters you have, how much data you can safely absorb. The more data, the better it's doing. Okay? But still, it feels very magical, right? This text-to-image models, you give them some prompt, something poetic, like the green creature made of leaves and vines bursting out in the ground, ready to attack. Like, imagine this for a second. Like, what would it be? And then you just give it to one of these things, and boom, it's quite magical, isn't it? Right? So where is this coming from? Where is this kind of a creativity come from? Well, that's the question that we wanted to ask. And so we decided to work on an area called visual data attribution. So there is a data set these models are trained on. Most of are trained on the data set called Lion, 5 billion images with a B, okay? And the question is, okay, which of these huge number of images have been most useful for generating this synthetic image, okay? So basically, we want to go and we want to find the influences from the training data on this generated image, okay? And I'm not going to tell you about the details about how we did this. It's reasonably straightforward. This is the paper. But here is the result. These are the 6 most influential real images for synthesizing this generative image, according to our algorithm. And here they are. Now, okay, maybe not so magical after all. First of all, I was kind of shocked that actually, these don't really look like photographs to me. These look like, paintings or something. So I didn't expect that in that big database, there is actually things that are not photographs, okay? And second, okay, so it's still kind of cool that it's able to do this. But maybe it's not that magical. Maybe it's not that surprising that out of these kind of data that the network, the model has seen, it's able to somehow interpolate something like this. Okay, so I have come up with a new saying, riffing on Arthur C. Clarke. Interpolation in sufficiently high-dimensional space is indistinguishable from magic. Okay, so it's basically, it could be that a lot of the magic that we're seeing comes from the fact that we humans, it's very hard for us to picture 5 billion images. And so we might not realize how much visual information there is in there that the model can use to put together the desired image, okay? And interestingly enough, that visual space maybe doesn't even need to be that huge. So this is something that is an old result from the 90s. In fact, I think it was in one of the distinguished lectures at the U where I saw this result. Back in the old days of active appearance models and active shape models and eigenfaces, the kind of magical result that if you basically take about 200-300 faces, okay, and you just basically put a linear subspace on them, essentially you can interpolate from these 200 faces, you can interpolate pretty much anyone else. Okay, now there's a little bit of, you have to do some, it's a little bit tricky, but it's not that tricky. It's basically you interpolate first in geometry space and then you interpolate in pixel space, but it's still, it's linear interpolation. It's something that you learn in linear, introductory linear algebra, right? It's very, very simple. And it's kind of magical that, we don't need that many faces to make any of the rest of us, right? And Vetter, of course, famously did this in 3D in the late 90s, also with about 300 people. And so first of all, it tells us that, there are more people than there are faces, right? That's also kind of explains why there are doppelgangers, just because, maybe the face space is not that rich. But also kind of, it tells us that maybe our visual world overall is, it's big, but maybe it's not that ginormously huge. Okay, and so this is kind of, so I couldn't, I know this is kind of a public audience talk, but I couldn't resist putting one of the recent papers that is going to be at NeurIPS this year in there. we basically said, okay, you know what? Maybe with this kind of linear interpolation idea, we can push it a little bit farther. Okay, so in the 90s, we were doing these kind of linear interpolation between faces. In the 2000s or 2010s, we were doing this linear interpolation in latent spaces with these GAN models. And now we thought, okay, why not do something even crazier? Why not do a linear interpolation between these neural networks themselves? These neural network models. What is a neural network? Neural network is basically you represented by, you know, a vector of weights, right? So these vectors, they live in some high-dimensional space. Well, we can interpolate between those vectors. Okay, it's kind of crazy, right? But what we showed is that, let's say that you have a bunch of networks. These are generative models. Each one is able to generate faces of a single individual. Okay, and it turns out if you have a bunch of them, in our case we have 60,000, although I think it would work also with like 10,000. We were able to interpolate the weights of these models to get a new model that would generate faces of me. And I was not in any of the training set, right? And it's kind of magical, right? This model basically, it was never trained. You just linearly interpolate all the weights, and it can produce infinitely many photographs of me. Maybe the world is not so complicated after all. Okay, so basically, the details are, you take a whole bunch of these models, 60,000 models, okay, and you put them all into one space, and you basically have a subspace. We call it weights to weights. And then you basically do interpolation in that space. Okay, how do we get these models? Well, we start with a basic model, stable diffusion model, and then we fine tune it for different individuals. So we have 60,000 different individuals, and we make a model for each one so that the model is kind of personalized to only produce pictures of a single person. And now we have 60,000 of them. Okay, and now we put all of these 60,000 into one space, and then we can do various things. We can sample new faces by just basically randomly picking a random place in the subspace and just creating a model from that, and that model is producing faces of somebody we've never seen before. Okay, we can edit. For example, we can say, okay, these are all the faces with beards. These are all the faces without beards. If you have somebody without a beard, we can add a vector, because it's a vector space. You can just add a vector that goes from no beard to a beard, kind of a beard vector. Just add it up, boom, move it over there, and magically, that person now has a beard. Okay. Interestingly, the other people that's not that person, they don't get beard. So it's just that individual. Okay. Or we can do the inversion, as I showed before. We take a single image and then basically solve for the coefficients to find a model that can produce that individual. Okay, blah blah blah. Okay, and so we can do this inversion. For example, given an image, we can produce a model that can generate infinitely many different versions of that face, and we can also do it for something that's not real images, but for example, cartoons or sketches. It basically just projects it onto the closest natural image, the closest photograph-looking thing, and it does pretty well. And also we did a thing, there's this theory that dog owners and their pets often look the same. So we decided to see what happens if the input is a dog, and then you project it down onto the human subspace and see what happens. Okay, and I think maybe, okay. Now, of course, this is all for faces. Faces are easy, as we knew, as we learned in the 90s. So we also have results in on other things like dogs and the cars and stuff like that. Okay. So, but still, linear or not, we still need the data. Okay. And so, in a sense, if you want to appear cool and smart, if you go to Silicon Valley and people ask you, okay, what do you think is going to happen to AI in the future? Very simple algorithm that would work for you is just look at how much data a particular task has. So for example, text data, lots and lots of data, great results. Image data, okay, not as much, but still a lot of data. Pretty good results. Video data, not that much, kind of iffy results. Robotics, basically no data and nothing works. Okay, very easy algorithm. Okay, and this kind of suggests that the Moravec's paradox lives on. Now, Moravec in the 80s made the statement called the Moravec's paradox. He said, in AI, the hard things are easy, while the easy things are hard. And the classic example of Moravec's paradox is this picture right here. This is 30 years ago. Garry Kasparov lost to Deep Blue. This was 30 years ago. Okay, but the important thing here is this other dude, the dude that moves the pieces. Still, there is no robot that can do that. Okay, 30 years later, and still there has to be a dude. This is kind of the Moravec's paradox, right? The hard thing, we thought that chess was hard, and turns out it was pretty easy for computers. But just moving the silly pieces still cannot be done in a reliable way. Okay, and indeed we are seeing kind of this thing right now. So here is a recent paper on basically giving all of these very smart AI generative models very, very simple tasks, like how many times does the blue and the red lines intersect? And they're not doing very well on it. Okay, so now this, of course, the solution to this is, of course, more data. And if you learned anything from this talk, it's really you add data and things become better, right? Makes sense. But let's think about kind of data availability going forward. So text data, I feel like we're getting to the end, right? Because we had about 2,000 years of human culture, and we basically all used it up. What's left is Twitter wars and Reddit posts. Not very high quality data. Okay, so my feeling is that while the text data was the biggest one, it's kind of finite. Okay. On the other hand, the data that comes from the natural world, images, videos, robotics, sensor, motor data, that's a much kind of lower quality data. It's much higher dimensional data. It's nastier, it's noisier data, but it's basically infinite. We can get infinitely many more of those samples. So I feel like if you are looking for like prediction for the future, my suggestion would be lay off text and start looking into these other modalities like visual and robotics, because I think that's where the exciting problems are going to start happening. Okay, so in the end, I wanted to close by mentioning this wonderful parable that my colleague Alison Gopnik at Berkeley, great developmental psychologist, talks about, called the stone soup AI. So in most cultures, there is this fable of a story of a stone soup. I'm sure you know it. The travelers come to a village and they're hungry and they say, "Oh, we need some. Do you have any food for us?" And the villagers say, "Sorry, no, we are poor ourselves. We don't have anything." And the travelers say, "No problem, no problem. We're going to make soup out of stones. Just give us a cauldron, build us a fire. We'll make an amazing soup. We'll feed everyone." And the villagers say, "Okay." So they build a big cauldron, put some big stones in it, and they're making the soup. And the travelers say, "Oh, it's going to be great. But, a little bit of salt and pepper would make it even better." And so somebody, of course, say, "Okay, I have some salt and pepper." And they say, but a couple of carrots, some sliced onions, maybe a celery stick or two, it's going to be even better. And then somehow they find that. And then they say, when we made the stone soup for the kings, we also put some chicken in. And that was amazing. And then somehow, of course, they find the chicken. And then in the end, the whole village is eating this soup. And they're, "Oh, this is such a wonderful soup." And imagine they made it just out of stone. So Allison's version of this is tech execs come to a village and say, we'll make amazing AI with just a few magical algorithms like gradient descent, transformers, and next token prediction. And everybody's, yeah, that's great. I say, but would be even better if we got ourselves more data. They say, okay, well, we'll have a little bit of data here. And they say, but even more magical with some human feedback to tell us we are on the right track or not. Okay. And even better if humans can somehow learn to ask just the right questions in just the right way. Right? And of course, in the end, the villagers are like, oh, what a magical AI, just from a few simple algorithms. Whereas, of course, all of these things have been the data that fed the stone soup AI. So in Gopnik's words, current AIs are not agents, really. They are cultural artifacts like the printing press, the encyclopedia, or the internet. Okay? So what about true intelligence? How are we going to get there? Well, we don't know. My feeling is that true intelligence must evolve from the ground up. We cannot start with language. We have to start with low-level signal and have it evolve on its own. And the best definition of true AI that I heard, actually, I heard here at the U, a young physics postdoc told me, AI is not when a computer can make poetry. AI is when the computer will want to make poetry. I think this is very, 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 very true. So, takeaways. So, is it all just data and there is no place for algorithms? No. Large-scale data is absolutely necessary, but it's not sufficient. There is plenty of other things to do if you are into algorithms. There is plenty of flight of fancy and creativity, and lots of good ideas will always be appreciated. But we need to learn to be humble and to give data the credit it deserves. Thank you very much. Well, actually, I don't really see well, so maybe somebody else can, yeah. The reason I do computer vision is because I don't really do have one myself. Oh, hi, great.
About synthetic data generation through simulation.
I'm suspicious. But, a good friend, good friends of mine, and actually some of my former postdocs and grad students have fancy companies that bank on that. The reason I'm a little bit suspicious is, well, where are these simulators going to come from? They're going to come from graphics. Now, graphics simulation, of course, it's good, but it's not amazing, right? There is still ways to go. But I think fundamentally, the main problem with these graphics engines is the same problem we have with everything else. There is not enough data, right? That's why the video games you go to, and they're kind of a little bit sterile. You go into your office, and the simulated office, it's like super clean desk. There is nothing, no trash in the trash can. There is like no piles of papers on the desk, right? It's all very, very nice. Why? Because all of this entropy, the artists need to enter by hand. Okay, so I feel like until we figure out how to import, how to scrape this entropy from the real world into the simulator, I think these simulations, especially for things that are important for like where you really need a lot of data, like manipulation, for example, I feel like it's not really going to get us far. And once we learn how to scrape all this data, well, we might as well just scrape it directly. And maybe then you don't even need a simulator. So that's why I'm kind of ambivalent about synthetic data. But I think my opinion is a minority one in this case. So I could very well be wrong.
So if you can have too much data, so you start to memorize everything, is that in the scope where you talked about? Do you see this as becoming like a long-term problem?
Nah. I mean, no, it's true that there's this wonderful short story by Borges called Fumes the Memorias, about a person who was kind of like Rain Man, and he would basically he was memorizing everything, but he couldn't make connections between what he memorized. So in that sense, yes, but I feel like if the task you're making the models do is a kind of like a prediction task, where you're training it to predict the future. The future is never exactly the same as the past. So if you think about it like a biological organism, how do we learn? Well, every piece of data is first it's test data, and then if you don't get eaten by the tiger, it becomes your training data. But it never repeats, right? Everything is going to be always a little bit different. And so the fact that it never repeats, I think, is enough to not worry about like just raw memorization, because it's always going to be somehow different. And so a good predictor will be forced to do some generalization. And one could say, well, humans do so great in their generalization. I'm not so sure. I think there is a little bit of a bias in the observation. We think about all the cases when we are very good at generalizing, forgetting about all the cases where we are really bad at generalizing. And in fact, I feel like maybe humans are okay in generalizing, but not maybe that fantastic.
Alex?
Sure, thank you so much. I was wondering, what are your thoughts on, is AI generated data polluting the input space that AI uses to train?
For sure. That is definitely, snake eating its tail. That's a big problem. In terms of visual data, so far, we have very good algorithms to tell if the images are fake or real. This is kind of actually surprisingly easy. In fact, we wrote a paper in 2019 saying, detecting fake images is surprisingly easy for now, and 5 years later, it's still surprisingly easy. That might not stay easy. We don't know. But for now, for visual data, it's not a problem. For text data, I think it might start being a problem. And I think at some point, either people will, be forced to train on old stuff or do some sort of, put some, some sort of certificates, some blockchain of something to make sure that it's real data. No, it is a problem. It is definitely a problem.
I asked a question on behalf of my student Harvey also. You showed data in different modalities. How about multimodal data? How can you learn across these data modalities?
Absolutely. No, I think that, in fact, I have used a lot of, I have done a lot of work on visual plus audio data. And that's very, very useful. And this is in fact like this is where self-supervised learning does the best, because you have multiple modalities that are talking about the same thing. They're sensing the same thing, except they're sensing it in very different ways. And those different ways are helping each other out. And so definitely the more sensors you have, the better. Now, a lot of the time people say that, okay, text is one of the modalities. That I would not agree with. I think text is a very different thing. Text is just much higher level signal. And at least in models that are using vision and text, vision and language just dominates. it's basically doing 90% of the lifting is done by language. Okay, where pixels are often just not even looked at, because they're just language is so much more powerful. And so my belief is that we in computer vision first needs to get our house in order with pixels and sounds and touch and proprioception, and only then go to language. Language evolutionary is 5 minutes ago basically it happened, right? But most animals have surprisingly good vision, and I wish we could do simulate a rat vision or a cat vision or something like this. So we have plenty to work on without getting to language.
So this is more for your speculation. You mentioned that you want AI to want to write poetry. What are the factors necessary to get there?
Again, yeah, this is total speculation, but my feeling is that, so right now, what we are training is this great simulacra, this cultural artifact, as Alison Gopnik said, that read all that we have written and is like like the Chinese room. It's able to answer very intelligently because of all the stuff it has seen. But it didn't really feel all what it has read, right? It reads about being hungry or being angry or being sad, but it has absolutely no way of knowing what that means. And it feels like to get there, you need to start much earlier. You need to start with some sort of primitive agents that have to deal with the real world, that have to avoid obstacles and run away from predators and find food, and only then do these notions of hunger and thirst and fear and happiness might emerge. And that's where you'll get something that's actually knows what it's talking about. But yeah, this is really like science fiction stuff.
Hi. Yes, I really enjoyed your talk, and I was especially intrigued by the sort of the quote you finished on, this idea of our existing AI sort of as a cultural artifact that kind of captures what we have sort of put out there as easily scrapable data. I wonder if you have anything to say about things that are reflected in the data, but we might have decided aren't good patterns that we want to be reflected in these agents. For example, stuff that, for example, in our history that perhaps now we've decided maybe we shouldn't have this be a part of what we do now, for example, or the things going forward in terms of things we don't think are great to preserve.
Things that are not great to preserve. So basically cleaning up your past data. I was born in the Soviet Union, and where, every time some dictator goes out of fashion, all of their monuments get taken away, and their entry in the encyclopedia gets cut out. Don't think that's the right way to go. I think, again, this is actually very similar to some of the approaches in robotics, where you do robotics by emulation. You basically you have humans drive the robot, and then you basically try the robot to kind of learn from that. So you get only the good stuff, but you don't get the bad stuff. And then the minute the robot is in a configuration that it hasn't seen before, it doesn't know what to do, because it's now in a space it has never experienced. So in my view, all of the bad stuff that happened to humanity is helping us avoid it in the future. So if you get rid of this, you're bound to repeat it. So I'm against censoring any kind of data, but probably good to have a little timestamp. This is what we did in the 14th century. We don't do this anymore.
We'll take one more question and then I'll be it.
So
When do you think we're gonna have the AI tell us how confident it is with the results that it gives us? So the confidence intervals or the errors, when will it be able to convey that to us?
I think there's already things that are kind of barking up that tree. It's, you can basically, solve, most problems can be solved several ways. And so if you try multiple things and you get to the same answer, there is a little bit more confidence. Now, I'm not sure that's kind of confidence interval really, but you get some sense of, okay, I got there for some reason. So there's something in my work that we've been excited about called cycle consistency, where we basically just try to, for any kind of hypothesis, just try to get back to a, use that to get back to their initial conditions and see if it cycles. And if it does, that's good news. And if it doesn't, maybe not. But I think the kind of interesting thing about these generative models is that as they get more and more of the kind of data that we also get, they become more and more behaving like us in good ways and in the bad way. Because humans are also really, really bad at giving confidence intervals, right? And it's maybe not that surprising that, we are very persuadable. We can, we change our mind all the time. Like all of the things that people complain about in these, all the LLMs, they also happen to humans. So maybe it's not that surprising because again, as the data that we're all trained on gets more and more similar, this kind of alignment is bound to happen.
Last question over here.
Do you have any ethical concerns about collecting too much data, visual, text, or any others?
No, I sleep very well at night. No such thing as too much data. In fact, when I talk to my psychologist friends like Odd Oliver, she believes that there is no limit to human memory. It is limitless. Now you might forget things by losing a pointer to that data, but at least nobody found an actual physical limit. Okay, you can remember that much and no more. So I think it's fine. It's just that at some point the memories are going to overlap and they're going to get noisier. But I think more data is always better.
Okay, well, let's thank our speaker. Great.